In this module, we'll be talking about vectors in cylindrical and spherical coordinate systems. Cylindrical coordinate systems. So let's say we have a point P in space, and we would like to locate that point with respect to the origin. So it can be located using three coordinates. First, we have the radial distance of that point from the z-axis. So we call this the radial distance. And the angle that this point makes from any radial line. So let's say this is a radial line that passes through the origin. So the angle, this angle, and the distance that this point makes from the xy plane. So this one. Okay. So this third coordinate is really the same as the coordinate used in the Cartesian coordinate system. So as we can see, the point P is also the intersection of three planes. We have the R equals R sub 1 cylinder. So the cylinder here colored blue, and also the phi equals phi sub 1 half plane. This one, so this one, and also the plane z equals z sub 1 plane. This one. So that intersection of the three planes locates the point P. Now let's say I have a vector uh, at point P. So let's say let's assume it to be the velocity of the wind again, and let's say it is shown here as this one. So that vector can be expressed by three components, just like the cylindrical or the Cartesian coordinate system. We can express it by three components. So let's call the vector a cyl for cylinder. So those components are a sub r, small letter ar, a sub v, small letter a v, plus a sub z, small letter az, where the capital letters ar, av, and az are called the component vectors of the original vector a sub cyl in the direction of the unit vectors a sub r, a sub v, and a sub z. The unit vectors has these following directions. So a sub r is always perpendicular to the cylindrical plane and lies along the phi half plane. So this one is always perpendicular to this cylinder and lies on this plane. A sub p is perpendicular to the phi half plane. So this vector here, this unit vector, is perpendicular to this plane and also tangent to the cylinder plane. And lastly, a sub c unit vector is actually the same unit vector as the Cartesian coordinate system. So a sub c really is the the combination of these three unit vectors along the a sub r direction, a sub v direction, and the a sub z direction. It is interesting to note that the two unit vectors a sub r and a sub phi are not fixed in direction. They depend on the value of the angle phi. So, for example, if the point is somewhere here, that would mean that phi would be here. So that means that our phi would be this one. Okay, so that will be our phi. Our r would be this one, and therefore the direction of a sub r would be in this direction. The direction of phi will be in this direction, tangent to the cylinder, and well, a sub z would still be in this direction. And this coordinate system is actually a right-handed coordinate system, and it's because that the cross product a sub r a sub phi will actually yield the unit vector a sub z. Vectors can be transformed from one coordinate system to the other. So let's see how do we convert from the Cartesian coordinate system to the cylindrical coordinate system, or vice versa. Let's say I'm given a vector in the Cartesian coordinate system, and I would like to transform that into a cylindrical coordinate system. So the way to do that is actually two steps. First, we compute for the components for the cylindrical coordinate system. So we have a sub r, so it's actually given here, a sub phi and a sub z. Well, a sub z is still the same a sub z in the Cartesian coordinate system. And then if the result is that it contains a variable coordinate, so we can use this transformation. So we note that x is actually r cosine phi, y is r sine phi, and z is still the same z. And also, if I would like to transform the cylindrical to Cartesian, I can also use this formula. So I will compute a sub x from this formula and a sub y from this formula. So the relationship again between the coordinates is that r can be computed from the values of x and y, and phi as well from the values of y and x. Now take note that the values for phi varies between 0 and 360 degrees, and it's always positive. Also, r is always positive because it varies from 0 to infinity. Well, z varies from negative infinity to positive infinity. A point can also be located using the spherical coordinate system. So let's say again we have a point P here. Now this can be located by three coordinates. So first we have the capital letter R, we call it the radial distance, but this time this is the distance from the origin up to the point P. Uh, the second coordinate is what we call the angle theta, and this is the angle from the z-axis going to the um, point P. So actually this is this angle here. And the third coordinate is the angle phi. the same phi that we have in cylindrical coordinate system. Uh, Similarly, the point P can also be located using the intersection of the three planes, just like the previous coordinate systems. So we have the plane created by the capital letter R, the radial distance from the origin. So that plane is actually a sphere having a radius of R, as shown here. So this is the sphere. The cone created by the angle theta. So these points here has an angle theta from the z-axis, and it actually creates a cone, a surface that looks like a cone, and another surface created by the angle phi, which is this space here, or this surface here. So this is the plane created by the angle phi. So the intersection of the three planes locates the point P in space. A vector can also be expressed as the three-component vectors under the spherical coordinate system, and those components are along the direction A capital R, A theta, and A phi, where the capital letters AR, A theta, and A phi are the components of that vector. The direction of the three unit vectors AR, A theta, and A phi are defined as the following. So A sub R here is directed radially outward and tangent to the sphere, and also lies along the phi plane and the conical surface created by theta, the angle theta. A sub theta lies on the phi plane and is perpendicular to the conical surface. So this unit vector, and A phi is the same unit vector as defined in the cylindrical coordinate system. We can transform Cartesian vectors in Cartesian and cylindrical coordinate systems into spherical coordinate systems and vice versa. So let's say I have a vector expressed in Cartesian coordinate system. To transform it into a spherical coordinate system, we can use these three formulas here. And to transform from spherical to Cartesian, we can use these three formulas. Also, if we need to express the Cartesian coordinate in terms of the spherical coordinate, we can use these formulas. So let's say we want to get the corresponding Cartesian coordinate from the spherical coordinate, we can use this. And if we want to get the spherical coordinates from the Cartesian coordinates, we can use these relationships. To assist us in the transformation of the coordinate system from one coordinate system to the other, we can use this table. So for example, my vector is given in Cartesian coordinates, and would like to transform it into cylindrical. So to get a sub r, that would be a sub x cosine phi plus a sub y sine phi. To get a sub phi, that would be a sub x negative a sub x sine phi plus a sub y cosine phi. To get a sub z, that would be the same as a sub z of the Cartesian coordinate system. Now, to transform the Cartesian to uh, spherical coordinates, so a capital R would be a sub x sine theta cosine phi plus a sub y sine theta sine phi plus a sub z cosine theta. To get a theta, that would be a sub x cosine theta cosine phi plus a sub y cosine theta sine phi minus a sub z sine theta. And to get a sub phi, that would be minus a sub x sine phi plus a sub y cosine phi. So this one is, this table is a very convenient table in facilitating the, the transformation process. So again, if there's a need to compute the coordinate systems from one coordinate system to the other, we can use this representation where we can derive the relationships. For example, I can compute for the x coordinate from small r, that would be r cosine phi, y would be r sine phi, and z is also capital R cosine theta, and here we have small r equals r sine theta. So let's have some few examples to illustrate vectors in cylindrical and spherical coordinate systems and the transformation amongst the different coordinate systems. So in this first example, we have points in space expressed in Cartesian coordinates, and we're being asked to um, convert their locations into cylindrical coordinates. So I'm just going to answer the first um point here, and I will leave the rest as an exercise. So to transform this point in Cartesian to cylindrical, I will just use this graphical illustration. So based on this illustration, the radial distance r can be found using Pythagorean theorem or the Pythagorean formula. So that will give us 6.4 units. To find phi, we can use the inverse tangent formula. So that would be the ratio y divided by x. And that will give us 38.66 degrees, or the point would be located in the first quadrant. Take note that phi here can be in four places: the first, second, third, or fourth quadrant, depending on the values of y and x. So if both are positive, that would be in the first quadrant. If x is negative and y is positive, that would be in the second quadrant here. And for x and y, both negative, that would be in the third quadrant. And if x is positive and y is negative, that would be in the fourth quadrant here. So we need to be careful using this formula, and we need to uh, locate the point where it belongs on the right quadrant. So the translation or the conversion of the coordinate system from Cartesian into cylindrical would be this one. For the second example, we have different uh, points in different coordinate systems. So this one is a point in the cylindrical coordinates. This one is spherical, and this one as well is in spherical. So we're being asked to transform the coordinates into Cartesian coordinates. So I will answer both A and B. So again, I'm going to use the graphical illustration. So, so to get x, I can use this formula. So that will be 0. To get y, I can use this formula. I will get this one. And z will be the same as the coordinates in the cylindrical coordinate system. So therefore, this coordinate in Cartesian would be this one. Now for letter B, the point is given in spherical coordinates. So again, using this figure here, we can get x, and that would be r, small r cosine phi. So that would be this one. Okay, but small r can be derived from here. So that would give us this formula, and that would give us this result. For y, that is also r sine phi. So this one, again, small r is given by this one. So therefore, we will get this answer. Z, on the other hand, is given by this formula. So that will give us this result. And therefore, the conversion, so this coordinate system in Cartesian would be like this. So in the third example, we have point P in Cartesian coordinates and vector A also in Cartesian coordinate system. So we are going to evaluate A, vector A at P in Cartesian, cylindrical, and spherical coordinate systems. Okay, so we have the vector A in Cartesian, and we want to transform it into cylindrical coordinate system. So first, we need to compute for the small r, the radial distance, the angle phi as well. So these are the values. So this is r, and the angle here is, the angle phi is this one. So take note that we made adjustments because x here is negative, so therefore the point P must be in the second quadrant. So that's why phi here is 108.4 degrees. Let me also compute for the capital R and angle theta, so that we can proceed with the transformation to spherical coordinates as well. So capital R here from the figure can be computed. So this is really the this R here squared plus Z squared square root, and we'll get this capital R. So it will give us this answer. And theta, which is always between 0 and 180 degrees, it will give us this answer here. So now we can use the table to compute for the components of the cylindrical of the vector in cylindrical coordinates. So this will be the formula. And as a reminder, A sub r can always be computed using this dot product, which will actually give you this formula. Okay, so so that will give us this answer. A sub p again is equals to the vector that the unit vector A sub p, and that will give us this formula as seen in the table, and that will give us this answer. Um, well, since A has no uh, component along the z-axis, well, that would mean that A sub phi here is a 0. So that would give us this answer for the cylindrical coordinates system. And for the spherical coordinate system, we can use the table again to compute for the components. So A capital R, that would be this one. A theta, that would be this one. And A V, that should be this one here. So this is our final answer for the spherical coordinate system. Now, as a check, we could also use the we could also we could also compute for the transformation to spherical coordinates using the values that we got from the cylindrical coordinates. So, for example, A sub r here can also be computed using this A sub z and the angle theta, so that will give us also negative 0.857, which is actually the same as this one. So that proves that our answer for the spherical coordinates is correct. In this last example, we have vectors, and we're being required to transform the vectors, into their spherical coordinate equivalent at the specified points. So for letter A, so we have a vector 10ax. So what is the spherical equivalent at this point? So to do that, we need to first compute for the coordinates r, theta, and phi, given the coordinates in Cartesian. So using this representation, we can derive those spherical coordinates. So we have these answers. So having computed the spherical coordinates, we can now proceed by computing the components AR, A theta, and A phi. And that would give us this vector in spherical coordinates. So this is the vector in spherical coordinates of this vector at this point. For the second vector, so that vector is given as 10ay at the point given in cylindrical coordinates. So therefore we have here Ax as 10, small r as 5, phi as 30 degrees, and z equals to 4. And again, using the graphical illustration that relates the different coordinates of the different coordinate system, we can compute for capital R, and because it is related to small r by this relationship, we can also compute for theta. Now that we have the spherical coordinates, we can proceed to compute the spherical components, AR, A theta, A phi, and that would give us this answer. So this is the vector in spherical coordinates of this vector at this point given in cylindrical coordinates. So for letter C, the vector is given as 10 Azā. So maybe this is in the form of Cartesian coordinates or cylindrical coordinates, since the two has the same components along the z-axis. And we are going to transform this into spherical coordinate systems at this point here. So the point is given in spherical coordinate system, so therefore we could immediately get the coordinates. And because of that, we could immediately compute for the components, and that should give us this answer. So this is the vector in spherical coordinates of this vector at this point. So in this video, we have discussed vectors in the cylindrical and spherical coordinate systems and the process of transforming in the different coordinate systems. Now in our next video, we'll be discussing about vector calculus.